So welcome back everybody for this afternoon session. We start with Sébastien Gouëzel from Rennes, and he will explain how to change variables in integrals and in lim.
Thank you. Thanks a lot for the invitation. It's a great pleasure to be here for this very nice day. I like to start with a basic formula for the Gaussian integral. This is a theorem, and you all know this, that the integral from minus infinity to infinity of exponential minus x squared divided by 2 dx. It's, I hope you all know the value here, that is the properties, and it's square root of 2 pi. If you want random variable, there are billion proofs of that, but the nicest one, I will be the following. You take the integral, you square it, and I will find that it's back. And how do you compute the square? Well, you say it's the integral with respect to x times the integral, say, with respect to y. And then you do some formulae, and so you have the integral with respect to xy of exponential minus x squared divided by 2, exponential minus y squared divided by 2, dx dy. And then here what is nice is that you have x squared plus y squared in your integral, and then you will change variables. You will write xy as r cosine theta, r sin theta, for r ranging from 0 to infinity, and theta ranging, say, between minus pi and pi. And so this double integral, this polar coordinates, it becomes the integral from minus pi to pi, the integral from 0 to infinity of exponential minus, well, x squared plus y squared, just the distance to the origin, minus r squared divided by 2. And then when you change variables, you have the Jacobian, and you get r, and theta. And then what is nice is that this does not depend on theta. So with respect to theta, you just get the constant. So it's 2 pi times, and then you have this integral with respect to r. And then what is nice is that here you have a function exponential minus x squared divided by 2. It doesn't have an obvious primitive, you cannot integrate it. But here you gain an r, and then this stuff here is exactly the derivative of the function exponential minus r squared divided by 2 to some side. And so just take the primitive of this function, exponential minus r squared divided by 2. 3 with a 2, it's okay. We take the value of this function between the value 0 and infinity, and so it's just 1. And that's the end of it. So that's a beautiful proof, very classical, very efficient, probably not very elementary, for 2 reasons. There are much more elementary proofs of this, because this uses Fubini here. Fubini is a complicated theory. I mean, measure theory is most of measure theory is easy, and Fubini theorem is not easy. But luckily for us, since my goal is to formalize things in MATLib, that's Floris here, and he's done Fubini. Thanks to Floris. I won't have to do it if I want to formalize. And then this was for the first time here, and then here you need to change variables. Change variables. And unfortunately, Floris is not interested in changing variables. That's the topic of my talk. I want to tell you how I formalize change of variables formula in Lyon, in this massive library that you have heard about this morning. And I want to write down some version that will apply in this situation, but maybe also in different situations. And I have to be honest with you, my end goal is not to prove this formula. I know much more elementary proof that just work with one variable, so just write down some differential equations. Blah, blah, blah. My long-term goal is to do Theorem homology on manifold, compact manifolds. And then you really want to be able to integrate differential forms. And just to see that the integral of the differential form is well defined, you know the chain of variables. And that's my motivation. And Theorem homology is a very long-term goal. This one that may look like a silly little theorem is not that simple. Just to give you some numbers about that. So this is now a theorem in MathLib. It got in MathLib in March 2022. But the project started some time ago because the first step into this got in MathLib more than 6 months ago, in September. It started in September 2021. And in between, there were 80 pull requests. What is a pull request? It's an elementary step in the process, or introducing some new notion. Each pull request gives rise to a referring process. People are nitpicking, saying this you can improve, you don't need the assumption, and so on. That's the way this library grows. People submit pull requests, and other people look at it, review it, try to improve it, and then when it has reached a good state, it's merged into the library and it's made available to everyone. So a project with 80 pull requests, it has to take some time. You can see 6 months, and it's not completely trivial from the point of view of the number of lines of code because it spans something like 14,000 lines of code, which may seem crazy compared to the simple theorem I'm talking about. But you'll see why in a few seconds. Okay, so let me just write down what I might mean by the change of variables form. Here is the standard version, one standard version of change of variables formula, the one you see in undergrad textbooks. It will be something like that. You take a space E, say you take Rn, finite n, with circular distance. For a space, you have the product of a measure. It's a measure. And then you take U, set of E, which would be an open set. And then you take some function f from Rn to itself, which would be, say, such that to restrict it to this open set Q, you get a diffeomorphism onto its image, and just get a simple statement. Let's say that it's a C2 diffeo V, which will also be an open set. And then what you have, that you can look at the measure of the image V, and the measure of V, you can read it at the integral value of the determinant of the derivative of f. Determinant of the x. That's just for the measure of the image, and then also get a version when we integrate functions. That's the integral of v of g of y dy. It would be the integral over u of the determinant of x times g composed of f x the u of x. Okay, sorry, try to write on the measure. And in fact, 2 is a pretty simple consequence of 1, because if you have that, 1 is a version of 2 for characteristic function of sets, and then with that, you make linear combinations to argue by density. And so this is a theorem, and 1 implies 2. That's standard, and I won't talk at all about that in the talk, and I will focus on discussion of this statement and variations of this statement. And I'd just like to give you a proof of this statement so that we are on the same ground of what is obvious and what is not obvious. So how can you prove that? That's really a statement you can prove undergrad, but if you want to really prove it, you have to be a little bit careful because things are not that obvious. When you're in one dimension, intervals are easy to manage. When you're not in one dimension, well, you like to do pictures, the pictures are sometimes a little bit misleading. So let me just do this. So, well, this section. Of course, I did pictures. I'm doing mathematics. And it's an open set, but I need to have some uniformity somewhere for conversion. So let's say that U is an increasing limit of a sequence of compact sets. There is no Kn. Okay. And I've drawn it like with squares because it's like that. So I claim that if you know that the measure of the image of Kn is equal to the integral of Kn, so the determinant of your map and the mu of x, I claim that it's enough to show that you have this and you compact set Kn, and the reason is that if you have this, you can pass to the limit, and when you increase Kn, the left-hand side will increase to the measure of b, and the right-hand side will increase to the integral of u because you have some kind of monotone convergence. So you just need to prove that. And how do you prove that? You have this Kn and you will cover it by squares like that. Okay. Take a small mesh. Take a small mesh M. And cover Kn by squares. And then, what can you say of so the measure, well, and say that they're disjoint or careful, you put on the left boundary, but not the right boundary, the BI, to make sure that you have the disjoint covering of Kn like that. And then the measure of f of Kn is just the disjoint union, so it's the sum of the measure of f of BI. And what is f of BI like? Here is BI. I take a point xi inside. And then here on BI, df is extremely close to df of x on this side. Why is that so? Because I'm on a compact set, n is small, and since I have taken this C2 control here, I mean that the third derivative is Lipschitz. So if n is small enough, the difference between these two guys is controlled by the mesh. So I have these two guys are close, and it's uniform over all I.
You mean to write df of xi and the right side?
Yes. df is essentially constant on a small square because it's a Lipschitz function. And what does that mean? It means that f of bi it will be essentially just like the image of bi under the differential here. It will be contained in say 1 plus epsilon, the rescaled version of df of xi applied to bi. And this is really straightforward from this behavior. And you also have an inequality in the other direction contained 1 minus epsilon df size. And this left inequality is harder because you need to know that f is essentially locally surjective, and that's here. This local surjectivity is a consequence of the local inverse theorem. It's fine, we are on an open set. So here we use a local inverse theorem. Local inverse theorem is already in math, so we check. So once you have that, you can compare the measure of f of bi to the measure of the image under the differential map. So the measure of f of bi, it will be comparable up to say 1 plus or minus epsilon to the power of some dimension. dimension. Oh, sorry, I have an n here and n here. That's really bad. So it's comparable to the measure of the bond. What?
It was a bound variable.
Yeah, still. So the measure here will be comparable to the measure of df of xi. But this is a linear map. We know how it rescales the Lebesgue measure. It rescales the Lebesgue measure according to its determinant. And so this is really 1 plus or minus epsilon equal n times the determinant of df psi times the measure of di. But again, since df is uniformly close to df of xi on this di, essentially this is uniformly comparable to the integral over di of that of df. So the integral of mu of x in mu of di and the integral. And so when I sum up everything, I will get that the measure of f of kn is 1 plus or minus epsilon some power times the sum of the measure, which will be the sum of the integral over bi of the stuff, with the bi in the form of disjoint partition of kn. So this is exactly 1 plus or minus epsilon n times the integral over kn of the function I'm interested in. That x.
When you write C2, C1 is enough, right?
Okay. For this proof, where I'm a little bit naive, I'd like to say that everything is uniform when my mesh tends to 0. All the squares work as well. And then here I need a good approximation which is uniform everywhere.
Your K compact, so it's
Okay, you're right. That's just enough. C1. Well, this function is continuous. It's uniformly continuous. We have seen that.
yes,
So C1 is enough here. And that's the end of the proof, because the theorem was arbitrary and we can get epsilon. So that's the end of the proof. We're happy. And then once you've done that, you can start formalizing it. But maybe you can do something better. Because here you see I have a lot of assumptions. And when you formalize a theorem, there is a gift that you can make to your users, is trying to weaken as much as you can the assumptions. So reason is that if one guy someday wants to apply a theorem, he will have to check a lot of things. He will have to check that Q is an open set. He will have to check that this function has a derivative. This derivative is continuous, invertible. He will have to check that the inverse map is continuous. That's a bunch of things to check. And maybe if this were true with weaker assumption, maybe I don't need the continuity of the derivative. Who knows? Maybe. You have a counterexample in mind, but maybe not. Maybe you don't need this to be an open set. Maybe you don't care that the derivative is invertible everywhere. Maybe you don't care that the inverse is continuous. Maybe you don't care about a lot of things. And if you could remove as many assumptions as you could, that would be better. From 2 points of view, from the mathematical point of view, it's always interesting to find the optimal assumption of the theorem. But really, in this kind of formalized mathematics we're talking about, it's really a gift you're making to the users of your theorem. Because if I remove assumptions here, it means that I will remove assumptions all the way down in all the applications of this theorem. Of course, if I just want to prove the initial formula for the Gaussian integral, the theorem is perfectly fine.
It's good enough. And you need to remove first to remove part of the domain, I guess.
Yes. Okay. I have to make a few comments on the weaknesses on this first theorem. And the first comment is that this theorem does not apply to prove the Gaussian integral of the Gaussian. So I will make some examples to show why this is not good. And here is my first example. Does not apply. Does not apply to so I'm not saying. Let's try to apply our theorem, this theorem to our situation before. What would you take? You would take U will be R2 minus the negative line. So this will be V. And U, it would be minus 5 I times the real line. And F of R theta would be R cosine, R sine. Of course, the integral over R squared, or if you remove this, it doesn't make a difference. So we have a function, it's a C1 differential in its image. No problem, the inverse is continuous, it's even C infinity, analytic, whatever. But here, you may have the impression that I'm in good shape to apply this theorem. I claim that this theorem still does not apply. And I'd be curious to see if anyone in the room can see why it does not apply. Even the formalizers. It's a problem. It's not a mathematical problem, it's a stupid problem.
So you require that F is defined everywhere?
No? Oh well, zero. I can, but okay, let's well, you can use this formula everywhere.
Okay.
Okay.
You didn't put multiplier on G. Maybe.
Okay. Here maybe I should be more precise. The statement is that for any measurable function G, the function here is integrable with respect to mu if and only if the function here is integrable with respect to mu, and then the integrals coincide. And that will be the case in that situation.
The back measure.
Ah, the back measure is fine. Okay.
If you prove that it's integrable,
Ah, it's integrable. No problem. Okay. The trouble is that here I'm lying when I wrote R squared. Rn for n equal to 2 is not the same as R squared. Because what is R squared for you? It's R times R. In the proof, I had two variables, x, y, and an element of R squared was a pair of x, y. When you want to apply a Fubini theorem, you need to be in a product situation. So I need to be in this setting. But Rn, what is Rn? Is the space of functions from set with n elements, say 1n. Wow. For n equal to 2, it's the space from the space, it's the functions from the space 1, 2 to R. It's not the same as a product. Well, of course it's the same in my mind. There is a canonical identification between the two of them, which is so canonical that we don't even think about it. But Lynn will not be happy if I put a theorem with functions from 1 to R and I want to apply it in a product situation. I will just tell me, I don't understand what you mean. These are not the same spaces.
But you can prove the theorem that R2 and R times R are the same.
No, they're not the same. There is a canonical isomorphism between the two of them. And maybe you could have this version and then you could say that this theorem transforms through this isomorphism. But then maybe the next day you will have RP times RQ and you would want to say it's the same as RP plus Q. It's not the same. Again, you would need to prove this identification to transfer. So here, a good version of the theorem would not be that. It would say let E be a general finite dimensional real non-vector space. Real finite dimensional non-vector space. But then you have a problem that you don't know anymore what mu is. Because on Rn, you know what mu is, it's a product measure. The n times product. In R2, you also know what the measure is because, well, It's a product measure. It's not the same as before. So the product measure in this space is not constructed exactly as in this space because it's just not the same space. But still, in mathematics, we have product measure for this situation also, thanks to Boris. But still, they're not the same. And if you want to apply that in a general finite dimensional vector space, there is no canonical choice of measure. So what would be the statement? Instead of taking the big measure, we say mu should be any nice measure. And what's a nice measure? It's a measure which is, say, invariant by translation. Take any measure. It's just something you need to have a nice formulation. And then, once you have this theorem, it applies the first example, and you can prove the quotient integral.
So now you need a theorem saying that in the one-dimensional, or in the R times R, the R measure is the same.
You need to know that the product of R measures is a R measure, and you know that the one-dimensional R measure is a R measure, and we have all that. Thanks for it. I said that a lot of times. Okay, so that's the first improvement you need to make to a first theorem, and you really need this improvement if you want it to be usable. Of course, in books, you will never see a discussion like that because no one cares. You know that if you have it in Rn, you have it in any finite dimension.
If you struggle and prove the first version, can't you just have a corollary, which is the second version, which only proves that any
yes, you can
deduce space is isomorphic to
yes,
Rn?
You can deduce the second version from the first version. Absolutely. And at some point, that's well, we will need to do something like that, because even when you want to prove the theorem for, say, when F is a linear map, okay, it should be obvious. You need to know that the linear map rescales the measure by its determinant. And to do that, you will work with matrices. So you will do that in Rn. And once you've done that in Rn, you will transfer it to any finite dimensional vector space by some continuous linear map. Okay, so that was my first example to show shortcomings of this version. But this version has still way too many assumptions. So here is another example. Take one dimensional, take f of x equal x cubed. Okay. And u will be -1, 1, and v will also be -1, 1, the image of u under this map. And then the change of variables formula is still true. The formula is still true. Well, of course, it's true because you can apply the theorem to the interval -1, 0, open. You can apply the theorem to the interval 0, 1. And then you can say that 0 in the middle is negligible. But you cannot apply directly the theorem because there is one point here where the derivative is not invertible. So this map is not a diffeomorphism on its image. So it turned out that it's general. You don't need a diffeomorphism here. You just need a C1 map. It's not important well, you have two things. It's not important that the derivative is invertible, and also it's not important that the inverse is continuous. Just remove it. And in fact, you don't even need the function to be C1. It's in order to differential. The derivative doesn't have to be continuous.
You still want a bijection.
Yes, you want it to be a differential map and injective. That's a bijection from its image. And now it starts looking pretty general, but you can even do better. You don't even need U to be an opposite. And maybe since I've changed so many things, it doesn't even deserve to be called theorem 8. It's a brand new theorem. And I'd like to write it here from scratch and call that theorem. Maybe this one you haven't already met because it's very much more general than the previous. be, what would it be like? You have E, so it's a finite dimensional, so I will need to be a normed real vector space. Why norm? Because I'm talking about derivatives, and to talk about derivatives, you need some norm, just to define the notion. Normed real vector space. Take F, the map from it itself. And then there is derivative, but there is a subtle business. So let me call the derivative G. You could associate to a point in E linear map. And you assume that you make some assumption. Sorry, I have a map.
You need a set.
And the set. And the set will be this. That first, step S will be measurable. Okay, for measurable, you I'm sorry, and mu is a parameter. So I want to say that this set is measurable, and here you have two slightly different notions of measurable. You have Borel measurable, it's a Borel schema algebra, or Lebesgue measurable, which means that you are allowed to add or remove bits of zero measure. And I like to stick to the Borel category because it's more convenient for a lot of applications. So S would be Borel measurable. And I will assume that on S, along S, F has G as derivative. What does that mean? You take some point in S, and you look at f of x plus h minus f of x minus, so the derivative would be g of x applied to h. And you want this to be negligible with respect to h when h tends to 0 and staying inside S. Okay? I'm only talking about the values of f along this set S. Along S, f as g has a derivative. And f is equal to S is in G. Okay? What are the assumptions? Yes?
Why real? Why a real vector space? Locally compact should be enough.
Okay, I'm talking about
Periodic.
change.
Yes, periodic fields. So
Periodic fields.
Okay,
it's the same proof.
Go back to work.
No, there is a difficulty in the way that linear maps rescale the measure. And it really depends on the field you're looking at and the vector space you're looking at. So I'm on shaky ground here. You're probably right. And maybe we can discuss that at the end of the talk. But okay, let's do it in the real case just for my own comfort.
I think it's the definition of the norm in the locally compact fields that is the factor by which the linear multiplication scales the raw measure.
Yeah, the definition of the norm and the dimension of the space. And then the conclusion is that then the image set f of s is measurable again, and its measure of f of s is equal to the integral of s of the determinant of g of x. And that's a statement that I have formalized, which is more emphatic. So, how did I come up with this statement? I don't know if it's a quality or a problem, but I'm really bad with literature. When I have a PhD student asking me a question, typically I will not be able to tell him to go and look at this book, but I will just be able to give him the proof. And so here is the same. Typically, I thought I knew what change of variables was, so I was able to write down the statement, and I was able to remove some assumptions. Okay, I was able to do it for differential maps instead of C1. I didn't need a homomorphism or whatever, but still I had this, no, I still needed C1, sorry. And I had this condition of open set because the proof I explained to you, it relied in an important way on the local inverse theorem, for which you need to have open sets. And so I was pretty happy with my statement with this open set. And I looked at two textbooks and it was what they done, what they did, you look quickly and got the questions he asked. And so I was pretty happy, but then maybe I should triple check what the right statement is. So I went to see on Wikipedia. And in Wikipedia, they gave a version like that. And I thought it was just a joke. Because if your set is not open, you cannot apply the local inverse theorem, and so you're doomed. It was really crucial in the proof. And so, okay, I will have to correct this Wikipedia article, but let's still check the reference they give. And they give a reference to a book by Fremlin on measure theory, where I say a book. It's not a book, it's a series of 5 books, each 1,000 pages long. And it's amazing. So I started looking at the books and really, we have a lot of things in that, in particular, you have a full proof of that. A full proof of that. And at first, I thought the guy was joking, and then I checked the details, and then I understood the guy was not joking at all. The guy was not joking, and still, it's very surprising because since you don't have this openness assumption, you really have to devise a proof which is quite different from the one I explained to you. And essentially, the tools you have here that in the proof sketch I gave to you, which we will try to mimic in a way, I told you that f of bi was contained in, say, a sketch version of differential applied to bi. So what you have is that the measure of f of bi will be bounded by 1 plus epsilon to the power n times the determinant of the f of epsilon. And the measure of bi, something like that. And to get inequalities like that, you will apply covering lemmas like Bezikovich covering lemma or Kitami or whatever. And for the lower bound, it's even more tricky. You will apply this, again, this Vitali or Bezikovich covering to some local inverse of f, but you don't have a local inverse because you don't have the local inverse theorem. But you have versions of the local inverse theorem that will apply to the restriction of f to some very carefully crafted subset of S. And that's the way he gets all these inequalities. And so that's pretty tricky, yes. So I'd just like to mention a few of the names of a few of the tools that show up in the formalization of this in the past. And maybe it will explain a little bit why you have 14,000 lines of code. So what did I need to formalize this theorem? Just a few keywords. Gaussian elimination. Because you need first to treat the linear case. And to treat the linear case, you want to show that the matrix with scales are measured by its determinant. And that's not part of the definition of a Haar measure. The definition of a Haar measure is invariant by translation. A matrix, how does it act? And to see that it acts like its determinant, what you do is that you take your arbitrary matrix and you decompose it as a product of transactions or whatever, and you see that transactions respect the double measure and diagonal matrices the scaling is the product of that determinant and so on. We didn't have Gaussian elimination at the time. Gaussian elimination is really important in undergrad curriculum when you want to solve simple equations, but in a big formalized mathematics library, really you don't need that. So I had to add a bunch of linear algebra around transactions and so on to have this Gaussian elimination to be able to apply it to my linear math. So from that, you deduce the scaling properties. R measures. For instance, the fact that the measure of a ball of radius 2 is 2 to the power of the dimension times the measure of the ball of radius 1. Something that is not obvious from just from the definition of R measure. And follows from what it's obvious if you can. It's just the application of a diagonal matrix, and for that diagonal matrix, at least in Rn, it's not hard because in R you know how to do it. And then in Rn you did use it in just a product measure. And then for a general vector space, you use an isomorphism with Rn. And you will argue that an isomorphism, this isomorphism takes R measure to R measure, and it has to be the same R measure as the one we know well, which is the product measure. So you need to know the uniqueness of the R measure on the locally compact group. Thanks, Floris. Once you have that, you're done for the linear case, essentially. And then if you want to go to the more complicated case, I told you, you need the covering lemmas for vector spaces. And so I did it with the Besicovich covering lemma. The Besicovich covering lemma tells you that you have in Rn, you have some set, and at each point of the set, you are allowed to use some balls with arbitrarily small radius. Then you can find a disjoint family of those balls that cover your set and whose measure adapt essentially to the measure of the set. So you don't have any overlap. And that's a nice combinatorial statement, and it's not easy, but I did it with the optimal constants because I'm a little bit crazy. And this optimal constant, it's a pretty recent paper, but with a very nice proof that can be from within. And then once you have that, you also need result on differentiations of measures. That means you have two measures, and you look at the measure of the ball of radius r for the first measure divided by the ball of radius r for the second measure, and you look at the ratio when r tends to 0, and this has to tend almost everywhere to the Radon-Nicolin derivative of the first measure with respect to the second measure, and that's something you need for this proof. Yeah. So I had to do that, and with that you also have argument of the density points sets in spaces. And then something completely unrelated, surprisingly, on descriptive set theory and Polish spaces. Polish spaces. What's a Polish space? It's a real name for a complete separable matrices. And why do you need that? You need that for the association here, which is something non-trivial. You have a Borel measurable set in a Polish space. You apply a continuous map, and the image will still be a Borel measurable set if your map is injected. And that's a non-trivial theorem. It's called the Lusin-Suslin theorem, and it needs a bit of descriptive set theory. Not so much, but still a little bit. Let me just, for my own pleasure, most of these things I knew, and here I already had to learn some new mathematics, and so I was very happy with that. So I just want to share my excitement with you. Did you know that you take F from E to F, where E and F are two Polish spaces, and you assume that this map is Borel measurable.
So what's the Polish space?
Yes, Polish space is a metric space or metrizable space for which the distance is complete and second countable. Okay, so all nice topological spaces you see are like that. Yes. I mean, if you're doing condensed mathematics, so Borel measurable map. Did you know that there exists another topology on E? Another Polish topology on E with the same Borel sets as the other ones, with the same Borel sets as original topology, for which your map becomes continuous.
We did the put back of the topology on.
No. This would only publish after. Okay, so it's funny for two reasons. First, the statement is funny. Who could believe that? And the second reason it's funny is because it's used in chain of variance form. We had expected that. Okay. And so then you have this Luzin-Sustin theorem I mentioned, for which you need things called analytic sets in logical spaces, and you don't want to know what that is. And so a bunch of effective set theory, but in the end it's okay. And then something trivial I should have mentioned, you need a determinant of a linear map on an abstract vector space. Because if you're on Rn, you know what the determinant is, you just take the matrix. But if you're in an abstract vector space, you need to choose some isomorphism with some Rn, take the determinant there and come back and check that this does not depend on the identification you chose. Even that was not in MATLib at the time. So in the end, okay, I put all that in MATLib, and these are all the, you need all this before you can start proving this theorem. So among these 14,000 lines of code I mentioned, this takes maybe 13,000 lines of code of prerequisites. And then the proof itself is not that long. And it's always like that when you formalize. Proving one given theorem is never long, but having all the bits you need for your proof is always going to be the longest part of the business. Unless, of course, everyone, someone like Floris has come and already made a good part of the job for you. If Floris hasn't been there, I should have multiplied this by 2. Why did I want to talk to you today about this segment? It's because it mixes a lot of mathematics. It's not a really deep theorem. It's not a research level theorem today, of course. But to be able to state a theorem, you need mathematics about what? Finite dimensional. You need a small bit of linear algebra. You need a little bit of topology. You have these non-vector spaces, and a little bit of descriptive theory of the Polish spaces. You need measure theory, you have the R measure. You need calculus, because I'm talking about derivatives. You need non-trivial integration theory. You need all these bits, and you need all these bits to play well together. And in computer science, often people insist that it's important that all the bits are independent one from the other, because then if you're not satisfied with one bit, you remove it and then use something else. And that's not the design we have in MATLib. We have one big monolithic library. It's called the cathedral model. And that's really important to play this kind of game. To play mathematics, you need that everything plays well together. And I think if you want to have a library which you are able to state and do that, you need to play with this cathedral model and not the other small module model. And another comment on this cathedral model is that I told you that in the end, my end goal is to do the RAM cohomology. For the RAM cohomology, I will need this. I will need manifolds. I've already done manifolds. I will need smooth vector bundles. I will need homological algebra. I will need a bunch of stuff. And the good news is that many people in this room are already working for me on the other bits I'm missing. For instance, homological algebra, you have thanks. Smooth vector bundles, Patrick. And all these bits, they will be coming together, and that's why my hope to have one day the RAM cohomology in Lyon is not crazy. All by myself, I could never do all this, but with the strength of all these great people, it's a realistic target. So now that I've given my general purpose, but I like to just go into one crazy detail in this. Okay, Just like in the talk by Ricardo, he has showed you some kind of tricks with this minus on the integers, on natural numbers, which has a little bit behavior. Here, there is also something weird that I'm hiding in the theorem. And since I have 10 minutes left, I can show you a little bit more. Tell you a little bit more. I'd like to take an example where this theorem applies. This example really is true. Let's see the theorem will be true. It has to be true because it has been formalized in. It was already in framing. This framing, guys, seems to be very difficult. Okay. This is my stupid example. It has to do with measurability issues. I hope you have a favorite non-measurable set. Here is mine. It's A. A inside R, it will be a non-measurable set. Okay? And then let me define some function from R squared plus R squared. F of x, y. Horizontally, I just put x. Vertically, I will kill y if x is in the set A. Or the opposite. 1A of x times y. That's a very nasty function. Because A is not measurable, so this guy is not measurable. And then let's still try to apply this theorem because we're crazy, and I never assumed here that f was measurable. Let's take S to be the real one. The horizontal real line. And then there is this map G that takes G of x, y. It has to be a matrix, look like a matrix. Let me take 1, 0, 0, and it's not very important here, but say 1 of x. Okay? A matrix that only depends on the x coordinate. And let's take let's theorem apply. Well, the line is already measurable. Check. Do I have this this behavior here? This differentiability behavior here? Well, I'm looking at points that have to be in S. So all the points I'm considering here, they have to be here. So the second coordinate has to be 0. So I'm only looking at the behavior of f along the horizontal line. And along the horizontal line, f is extremely nice. It's just the identity. And it's just the identity. And g of x h, x and x plus h, they have to be in the horizontal line. So the difference between the two of them is also horizontal. And so when I apply g to this horizontal guy, I'm just seeing the entry here. It's just 1 along the horizontal line. This is the identity, and I'm fine. So all the assumptions in the theorem are satisfied. And of course, f restricted to S is injective, it just happens. Then the claim is that what? The image of S under F is Borel measurable. It's true. It's just again the horizontal line. It's fine. It's measurable. That's true. Of course, that's true. This theorem is true. And the Lebesgue measure of the image is just the integral along this horizontal line of what? Of determinant of G. But the determinant of G is something crazy because it's this not measurable function. 1A of x times x. And then you may complain, what are you doing? You're integrating a non-measurable function. Of course, I never claimed here that my function was measurable. I never said that this function is measurable. In a sense, here I'm really stupid. Because since I'm only talking about differentiability along the horizontal line, what the matrix G does on the vertical line is not relevant to the statement. So in fact, G is not unique. I could have used, if you take G tilde of xy equals 1, 0, 0, 0, it could just satisfy the assumption of the theorem as well. This does not determine the derivative in a unique way. And that's why I wanted to choose some G and not talk about the derivative of f.
It is a Lebesgue measurable.
It's Lebesgue measurable. But I was careful to stay in the Borel category here. Okay, but of course you're right. The point is that, okay, this function is not measurable, but I'm integrating on a set of zero measure. And of course, when you're integrating on a set of zero measure, whatever you put inside, you want the integral to be zero. So if you give a meaning to that, d should be 0 and d should be 0 and you're set. But of course, it will depend on the definition of your integral. You have to be careful to define the integral well enough to make sure that the theorem is true. If you take a random definition of the integral which is not the right one, your theorem will not be true. And if you take a definition of the integral which is the right one on measurable functions, but not the right one on non-measurable functions, say something which is equal to 1 for all non-measurable functions, your theorem will just plain wrong. And so there is some subtlety in the definition of the integral. And in fact, it's known that the definition of the integral in MathLib has gone through 4 revisions. Because each time we have seen that the previous definition was not perfect in some respects. Some theorems that should have been true were not true with our definition. The first one and the second one. So, and I'd just like to give one crazy example, which failed with our third definition. And that came, we realized that much later after the definition. And we only realized that when we were formalizing more advanced. So what is the theorem that I'd like to be true? Take I want to take two functions f and g from the real line to the real line. And so they are both continuous 0, 1. And I want to say that the g is, f is the derivative of g, so g of x plus h, and the g of x divided by h tends to f of x for x in 0, 1. And so when h tends to 0, and I want x plus h. F is the derivative of g. And then, hopefully you believe me that f is the derivative of g is the primitive of f, so hopefully g of 1 and g of 0 should be the integral of 0, 1 of f of x dx. Okay? Hope you believe this is true. And this was not true with our first definition of integral. What was the issue? The issue was, okay, when you write down some integral, you want to say, if my function is nice, then the integral is what you expect it to be. And if the function is not nice, you still want to be able to write down the integral, but the system will return some value which is chosen more or less at random, just because we want to have the right to write down an expression. And so what we decided is that if f is not measurable, set integral of f du equal to 0. Otherwise, set integral of f to be equal what it should be.
Measurable in Borel.
Yes, of course. What it should be. That was our first definition. Note that here, there is no guarantee here that f should be Borel measurable. Because I'm just requiring that it is continuous in 0, 1. I'm not saying anything beyond 0, 1. maybe between 1 and 2, it's completely wild. Now, of course, we don't care, because here it's only talking about the values of f and 0, 1. But with our original version, with this definition of the integral, this theorem is just not true. Because f is typically not Borel measurable, so this thing would be 0. There is no reason why the left-hand side would be non-zero.
But isn't
So
integral of 0, 1, doesn't it mean integral of f times the indicator function of 0, 1?
No, because that's a good question. What this really means is that it's the integral of f with respect to some measure, which is the Lebesgue measure. Okay, this is a measure, and you integrate to function f with respect to this measure. It's better to use that because with that, all the general theorems on integral will apply to set integrals like that. If you put in some indicator, we need to reprove all the theorems for general integral to set integral. So that's really a better definition, but then f is not that measurable. So we change when we arrive to formulation of the fundamental theorem of calculus. We revisited the definition of the integral to replace Borel measurable by Lebesgue measurable, as you suggested. And then
but can't you combine the two? So can't you define the integral to be f times the characteristic function against no, because this is on the whole. Yeah, okay.
So we revisited the definition to replace Borel measurable by Lebesgue measurable. And even later, we revisited again the definition to also allow functions that take values in non-separable Banach spaces, where you need to be even more careful. And what you want to be able to define the integral of your function, what you want is that your function is almost everywhere equal to a Borel measurable function taking values in a separable subspace. And that's the condition we have now, and that seems to work for all applications. And I'm already over time, so I'll stop here. Thank you.
Other questions? Yeah.
So does Fremlin also return a garbage value for integrals, non-measurable?
Okay, I cheated a little bit. The version in Fremlin, he does it for Lebesgue measurable functions, and he assumes that his function is Lebesgue measurable. One thing that I didn't tell you when I wrote the theorem is that this change of variable formula, it even works when your function is not measurable or not integrable. Because since you have equivalence between integrability on one side or the other side, if one side is not integrable, the other side will not be integrable either, and so on both integrals will be the junk value 0, and so the integrals will still coincide. So when you want to apply the change of variables formula, you don't need to check that your function is measurable or integrable or whatever. It's true all the time.
No, but it's a consequence of the theorem is that G is necessarily Lebesgue measurable.
Well, in the proof, you prove that G is Lebesgue measurable because, in fact, I gave you an example where G is not uniquely defined along the real lines. But if your set has tangent directions which are not in the line, if they span the whole space, then the derivative has to be unique. And at Lebesgue density points of a set, you approach from essentially most directions, so the derivative will be unique. In fact, on the set of Lebesgue density points, your function will even be Borel measurable. And since this has full measure in S, that's part of the proof. It's not scary, it's fun.
No, what I find scary is that, that if I want to check my proofs,
no,
and,
you don't.
maybe
You don't
somebody
have
defined that
to
this
do
is
that.
0.
Maybe
If it's not defined, then
I should make a comment that it's important to pay attention to these crazy details when you're building a library, which is designed to be used by many people. And then you really want to remove all the surrounding assumptions and so on. But if you're just formalizing your own theorems, just put the assumptions as strong as you like, if it just suits you.
Nobody's worried about the junk value. Maybe you will prove that two things are equal, but only because they are both not defined actually.
Yeah, because for example, in the video, I said that you can eliminate conditions, necessary conditions. But maybe I would just think, well, let's eliminate something and it still works. But it's just because it would give me
Okay,
a junk value
it's-
that would
it's-
realize that it's a junk value and then the grade.
It's really important to get the right definitions, because I could define the integral of a function to be always 0. And then many theorems would be true, but that could not be very
It's
satisfactory.
strange to want to define the integral of function that is not measurable.
It's not that I want to define them, it's just that when I write integral of f times some measure, it has to make sense for all functions. Otherwise, you could have a different point of view that whenever you write this, you would also have to provide a proof that your function is measurable on the package. And that's
That's what we do in math, right?
no. When you write on a paper, there is always the implicit promise that you make to the reader that all the functions you write down are measurable.
I agree. We do not prove it, but we never write integral of f if we are not convinced that f
Yes.
is measurable. Whereas
Absolutely.
here it's a different point of view. You're saying that you want to write integral of f, whatever f, and you just have a guarantee that this is what you want when f is measurable.
Yes. So when you write down your theorems, since you will just apply it to measurable functions, everything is fine.
Yeah, you can put in the conclusion of your theorem that f is integrable and integral of f is
Yes. In fact, that's typically what we do when we prove the real formulation of the chain of variable theorem is that if g is integrable, then g composed with f times the determinant is integrable and the integrals coincide. Of course, that's the way it's written.
But the point is that otherwise, like if we only define integrals for measurable functions, then you get really ugly notation. I mean, you cannot use an integral sign because the integral sign doesn't have a location, like a physical location where you put the proof that f is measurable.
It becomes very much more painful than to have a total function. Not just the promise, the implicit promise.
So we're not encouraging people to start integrating non-measurable functions. But we do want to allow them to write down the integral without.
So if you have a theorem which says integral of f equals to 0 and it's correct, it only says that either f is not measurable, or either you're not proof that it's measurable, or
No,
it's not measurable or
mathematicians never write down integrals like the integral doesn't exist. For example, in the proof of Fibonacci theorem, like on a set of measure 0, like the inner integral might not exist. And like careful proofs of the Fibonacci theorem acknowledge that and prove that like this only happens on a set of measure 0. So like even in even in cases like that, you actually want to define your integral when in like a set of measure 0 it might not make sense.
and again, if your theorem is claiming that integral of f is 0, then the conclusion should be f is integrable and integral of f is 0.
And let me just for fun write down something that the integral of minus f is always not minus integral of f. But the integral of f plus g is the integral of f plus integral of g when f and g are integrable. Okay? So when you want to put a sign out of an integral, you don't even need to check that your function is measurable. But if f is not measurable, this one is not measurable either, and both equals to 0, and minus 0 is
I would prefer more checking to be convinced that what I'm thinking about is true instead of having.
The fact here, of course, in the library, we could have this theorem with the additional condition that f is integrable. But I'm thinking of the user, and the user he really wants to go as quickly as he can. So if he can dispense with checking something, that's very good.
I had a question. You were talking about this Lebesgue differentiation theorem. So,
Yes.
are we far of getting other almost sure conversions or other maximal inequalities that are very used in harmonic analysis or
You mean
martingale convergence theorem?
inequalities
or
or
inequalities?
no, these are not hard. I mean, once you have Vitali or Besikovic, Hardy is really easy, and Martingale, you just need to prove the maximal inequality, and it's not hard. We have Martingales, so I think Martingale convergence theorem is just a few days of work ahead, and we just we are about to get stronger part numbers, so we have on the way.
I also have a question about the future work. So Are you now interested in proving Sartre theorem, especially the intersection with the kind of arguments?
There are many things that would be interesting to do. Right now, I have to finish writing 3 papers with 3 co-authors who are bothering me a little bit.
So you should ask them to formalize
You're
that part
recorded
of the
now.
paper.
You cannot promise.
So no, but what? Okay, you have to set on some priorities, and I think my priority is really to get the Theorem cohomology. So how far are we from the Theorem cohomology? Well, first I will have to understand your homological algebra library written in categorical points of view, which I don't really know. But if you give me a down-to-earth version, we need a little bit of differential calculus, a little bit of smooth vector map, which shouldn't be that far away.
Yeah, I think so. Then get up super.
A lot of exciting work.
Okay. So we can thank Sébastien again.